This webinar is dealing with precipitation from space, using the different parts of the electromagnetic spectrum in order to derive precipitation. After a short introduction, we will discuss some of the precipitation retrieval principles, as well as the algorithms and how do we visualize precipitation, and finalize with some conclusions. I hope that after this presentation you will have some idea on the principles of precipitation retrieval, a number of precipitation algorithms and visualization methods. It is good to have first a small view on the weather and the role of clouds and how these are observed by satellites. The incoming solar radiation can, if non-obstructed by clouds, can reach the Earth's surface, both the water as well as the land. With existence of clouds, of course, that radiation is being reflected by the clouds. Solar radiation causes heating and therefore evapotranspiration over the ocean and the land, resulting in water vapor in the atmosphere. Given an uprise of our warmer air mass, this, after condensation of the water vapor in the atmosphere, is causing clouds. When the temperatures in these clouds get lower and lower, the water vapor transforms into ice crystals, larger ice crystals, and eventually might cause rain if sufficient supply of crystals or water vapor is added to this cloud system. Clouds both reflect solar energy, but also emit. At this moment, we have a number of geostationary satellites situated over the equator, as well as a number of polar orbiting satellites at lower altitude, which provide us with continuous observations, especially from the geostationary satellites. The polar orbiting satellites are restricted to less observations, but because of the number of polar orbiting satellites, we still have a reasonable amount of observations at lower altitudes at our disposal. Shortly talk about precipitation retrieval principles. So what is the effect of clouds on the different parts of the electromagnetic spectrum? How do the hydrometeors within the clouds interact with microwaves, and what do we observe by satellite if we compare it to ground-based observations? When dealing with visible and infrared algorithms, the assumption is that the cloud top temperature is related to the cloud height, which in turn is related to the cloud thickness and to the rain rate. So the general principle is the colder, the brighter the clouds, the more heavier the rain. The warmer and less bright clouds are associated with light or no rain. This is a reasonable assumption for convective clouds, but a very poor assumption for stratiform clouds because they are relatively warm, but cause rainfall. And on the other hand, when we talk about cirrus clouds, they are cold, but they do not provide any rain. So here you see an illustration of this, where on the right-hand side you see a decline in temperature over altitude, and you also see the different cloud systems So for the cumulonimbus clouds, the assumption is, well, the cirrus cloud is not causing any rainfall and the nimbostratus cloud is relatively warm, and therefore the relationship with cloud top temperature is not fully valid. On the other hand, we are also using the microwave domain. Ice in clouds is scattering the terrestrial radiation downward. So in that case, if we look at the top, it's producing cloud areas at the top of the cloud. So we can relate the rainfall rates to the difference in brightness temperature from the cloud in relation to the surrounding area. So we can, if using high frequency channels, we can apply it both over land and over ocean. The weakness is that it's poor at detecting precipitating clouds with little or no ice, as is the case with orographic precipitation. On the other hand, when using the microwave domain, we can also have a look at the emission. So water in clouds emit radiation. So therefore, there are slightly higher temperatures over the clouds compared to the background. So again, we can make a relationship between the non-clouded and the clouded areas and use the brightness difference, the brightness temperature difference. So the cloud, even if it is having little ice, it can be used. When over the land, the problem is that the emission is very, very variable, and therefore, in general, this method is applicable over oceans, but not over land. Again, a small illustration. On the left-hand side, you see the scattering principle, resulting in a lower brightness temperature above the cloud compared to the surrounding area. On the other hand, if you look on the right-hand side, you see that the water vapor is adding to a higher brightness temperature above the cloud compared to the areas which are non-clouded, in this case over the oceans. In general, we have the energy from the sun, which is interacting with the cloud, and based on the spectral characteristics by our sensor, we are recording the reflectance and the emission, and we try to derive an idea about the geometric thickness, the thermodynamic phase, so if it's consisting of ice or water, the optical thickness, what is the radius, and the droplet distribution of the particles, the hydrometeors within the clouds. And we try to link them with the observations on the ground to derive the rain rates. It must be said that if we compare the visible near infrared or infrared with the microwave radiances are more sensitive to moisture throughout the clouds, whereas the infrared or the visible is directly related to the conditions at the top of the cloud. And the rainfall processes in order to actually monitor the rainfall processes, we have to have an idea of what is actually happening throughout the total cloud body. On the other hand, the visible thermal infrared is observed by geostationary satellites at a very high temporal resolution. So short timescales, whereas the microwave instruments are restricted to polar orbiting instruments, and therefore we have limited observations. And it might be that given those limited observations, we totally miss the occurrence of precipitation because it happens in between the satellite overpass. There are different precipitation algorithms as well as the combination of those algorithms through a blending procedure. Traditionally, use is made of the weather radar, where the radar system emits radio waves. Part of the radio waves are backscattered due to the interaction with the hydrometeors within the clouds, and that amount of backscatter, so the reflectivity, can be related to the precipitation rain rate, as the higher the backscatter, the higher the precipitation rates. There are issues, especially when we are dealing with light rainfall detection, but there are also issues related to radar range, the angle in which the beam is transmitted, and also related to shadow in mountains, so radar shadow, as well as noise in the signal. But in general, the weather radar is an instrument which is widely used. And here you see an animation of the high temporal observation capability of the weather radar, in this case over the Netherlands. And here you see an integration of all these weather radars over Europe. These are not readily available in Africa. So therefore, a number of other observation techniques are being applied, and one of them is making use of the SEVIRI instrument on Meteosat second generation. The geostationary satellite with a 3-kilometer sub-satellite spatial resolution with quite a number of spectral channels with an observation capability every 15 minutes. We are observing through the visible, the near-infrared, the water vapor channels, and the thermal infrared parts of the electromagnetic spectrum, in conjunction with a panchromatic high-resolution visible 1-kilometer spatial resolution image every 15 minutes. Over that electromagnetic spectrum, you see over here the irradiance and the radiance, as well as the absorption through constituents in the atmosphere like water vapor and carbon dioxide. And the windows of the spectral channels are being provided here as well for the different channels of Meteosat second generation. You see that a number of channels are included in the water vapor domain, so the so-called water vapor channels. There are other channels which are specifically designed to include also the absorption caused by carbon dioxide, as well as those channels which are in the outside these atmospheric absorption windows. So the combination of these spectral channels allow us to use them for the purpose at hand. Looking at some of the spectral characteristics, here an example is given of snow having different radius. You see that there are different reflectance characteristics of these snow particles having different radius over the various spectral channels. So we can use those in order to discriminate and say something about the radius of particles. If we look also with respect to the difference of absorption of water and ice, you see that, for example, in the 1.6 micron channel, there is a strong difference between the degree of absorption of water compared to ice. Ice is a very strong absorber. So these differences can be utilized. Apart from that, we have on the geostationary satellite different spectral channels which are providing us information not only of the Earth's surface but also of the atmosphere, which is reflected by the normalized weighting function. So in the case of the water vapor channels, the maximum contribution of the signal which we record by the satellite is not coming from the ground surface here given at 1000 millibar, but is coming from within the atmosphere at a certain pressure level, here at about 350 hectopascal. And if we also look at channel 6, which is also in the water vapor region, then we see that it's coming from a different pressure level, which can then be transformed into the elevation above the Earth's surface. It can be seen, for example, that the IR 10.8 is basically having its maximum contribution from the Earth's surface. So we have, by utilizing the different spectral channels, we can incorporate also what is happening within the atmosphere. We are utilizing these to prepare our quantitative retrieval algorithms. So we try to relate the spectral radiances to physical parameters. The strength is that the methods are physically based. We get quantitative information which is comparable in space and time. The weakness is that the success of it depends on the calibration, and assumptions within the model can of course deviate from nature, and calculations do require computing resources. Here you get an example of the SSMI on board of the Defense Meteorological Satellite Program, which is using different frequency channels in order to observe the atmosphere. Using the principles of emission and scattering, in that way trying to record the radiation emitted from raindrops and scattered from ice particles, as well as the radiation for high and variable emissivity. So both over oceans only, as well as land and oceans. So here you see the 19 gigahertz compilation over a day. For detection of precipitation over the oceans only. And the higher frequency to detect the precipitation over land as well as over ocean. But you still observe gaps in the observation frequency even over a day. And this is where the Meteosat second generation comes in, as we can co-locate in space and time the observation from the SSMI and relate that to the cloud top temperature, and trying to relate the intensities as they are being recorded by the SSMI to the cloud top temperature, and then merge it with the temporal resolution of Meteosat second generation to get a higher order rainfall product. That same principle, but only incorporating many more different observations from geostationary satellites as well as from polar orbiting satellites, incorporating the global precipitation monitoring mission, allows us to get an integrated multi-satellite retrieval product, IMERG, to get an idea of the precipitation over the majority of the Earth's surface. There are issues with respect to blending, because initially there might be low correlations because of the spatial and temporal offsets. And averaging procedures are being applied to correct for these offsets in order to get better correlations. A technique that hopefully is going to be applied more and more in the future, especially over areas where there is a limited ground observation network, is the use of telecommunication microwave links, as the rainfall in between the transmitter and the receiver cause an attenuation of the signal. And that attenuation can be directly related to rainfall intensities. And this, in conjunction with observations from geostationary satellites, might then be used in order to get a better idea over the aerial rainfall in a certain region. Here you see an example of such a network. So mobile telecommunication network could be a very good replacement or addition to station-based gauge observations. So how do we observe clouds on satellite images? Here you see a panchromatic image on the left-hand side with a 1 kilometer spatial resolution subsatellite, as well as the multispectral lower 3 kilometer subsatellite resolution color composite of the visible near-infrared channels. So there is a great detail on geostationary observation at 1 kilometer resolution. We can combine the near-infrared, the visible parts of the electromagnetic spectrum, into a color composite, resulting in a coloration of clouds which shows you those clouds which have or contain at the top of the clouds ice, warm clouds which are white, which contain basically water droplets, Snow can be detected given the different texture, as well as fog also having a very clear signature. So the visible near-infrared cloud visualization. We can also have a look at shape. So you will be able to have an idea about the frontal systems which are elongated, especially seen at the higher latitudes, in combination with those which are, let's say, circular shaped, which are more convective type of systems, together with the coloration, as in this case the cyan colors are an indication of a strong reflection in the visible channels given the absorption of ice in the near infrared. We can of course also use the temperature provided by the 10.8 micron channel, and again the circular shapes of the convective systems in conjunction with the color, here reddish, which is an indication of strong reflection in the visible channels, and a low contribution because of the very cold cloud tops in the thermal infrared part of the electromagnetic spectrum. Overnight, the visible part of the electromagnetic spectrum can't be used, so we can make a utilization of the thermal domain only. And also over here, using band differences, we are able to get an idea about features within the clouds, like medium thick clouds, or thin clouds. Band difference combinations can be used also during daytime. So having differences between the near infrared and the visible, the shortwave thermal and the longwave thermal, as well as the difference within the water vapor. So the different sensitivities can provide us with an idea of droplet size, water ice phase, and alike. Some examples of retrievals. A very simple one is just making use of the thermal infrared and the water vapor, where small brightness temperature difference between the two give us an idea about potential precipitating clouds. And you can compare the left-hand image with the right-hand image, where the blue sections have been classified having a brightness temperature of less than 11 Kelvin. Another one is related to how long a cloud remains below a certain threshold temperature. So the top of the cloud is more cold than a given threshold, and that can be related, so the cold cloud duration can be related to the rainfall intensities. This is a procedure that has been applied already for quite a long time. Another one, which actually is a kind of predictive measure, is the use of stability indices, or the convective available potential energy. So the atmosphere or let's say the instability of the atmosphere and the updraft potential within the atmosphere. If there is a strong updraft potential, so a strong buoyancy, that can give rise to warmer air parcels, which are then cooling very rapidly, and those can cause heavy precipitation in the near future, so within the next couple of hours. So these global stability indices in conjunction with the CAPE are qualitative indicators which are used for nowcasting to say something about what could happen over the next couple of hours. Using reflectances by, in this case, Meteosat second generation, the 0.6 micron in conjunction with the 1.6 micron over land or over sea, the reflectances can be transformed into effective radius and the cloud optical thickness. Having these parameterized, these can be used to derive the cloud optical thickness as the effective radius, the cloud phase and the cloud top temperature as being first order retrievals. Together with other algorithms, these can be transformed into second order retrievals, whereas the one of our interest is the precipitation rate. So in this case, the cloud optical thickness, the effective radius, the cloud phase and the cloud top temperature would allow us to derive rain rates in a quantitative manner. You see here the observation as from the weather radar in conjunction on the right hand side with the observation transformed to rain rates by Meteosat second generation. And here you see it over West Africa, where you see the continuous observations of SEVIRI, resampled in the center to a coarser resolution in order to be able to compare it with the TMI. And the TMI is passing over only at a certain moment because it's a polar orbiting instrument. To conclude, the meteorological satellites have become increasingly important. The observations from clouds to derive precipitation require frequent observations as they are observed from geostationary satellites. Depending on the applications in mind, the observations from meteorological satellites can be used qualitatively as well as quantitatively. For quantitative retrievals, take into consideration that those are sensitive to errors and require accurate instrument calibration as well as model calibration. Thank you for your attention.